And looking at the periodic table, we will see silicon and germanium are the two main components that we use, or main elements that we use in order to make semiconductors. We either use silicon or we use germanium. The reason for that is they've got 4 valence electrons. Basically all that means is on the outer layer of the atom there are 4 electrons, which has the ability to bond with other elements. Left of that we've got boron, aluminium, gallium and indium along with others. Those are all my column 3 elements. Then column 3, because they've got 3 valence electrons on their outermost shell. On the right hand side of silicon and germanium there's a whole bunch of other atoms, but we're looking at phosphorus, arsenic, antimony and bismuth. Those are all in column 5, and the reason is they've got 5 valence electrons which they use to bond with other elements. Now, as I said, silicon and germanium are the primary building blocks of all semiconductors. So when we've got our silicon or germanium atom and we've got it in its purest form, we see that we will have a lattice whereby it has layered itself in such a way that it'll have the atom with 4 electrons around it in the valence track or the valence shell. And when we look at the combination of the electrons, this goes on all the way around. When we look, we see that this pair of electrons are going to bond these 2 elements together. That pair of electrons are going to bond those 2 atoms together, and so on and so forth all the way around, and so on with other elements. Now, when I take my column 3 element and I insert it into this crystal lattice, what we find is it only has 3 electrons. And those 3 electrons will bond with 3 of the elements around it, but we see over on one of the 4 sides that there's an electron that doesn't pair bond with my column 3 element. Now, that place where the electron can go, we call a hole. Okay. Now, that hole is just a place where there is space for an electron. And if we look at this entire grouping, we will find that each element that we used is neutral as it goes into this mixture, but at the end of the day it is still neutral. This type of configuration, this type of combination of elements, we call our p-type material. Not because it's positive, just because it is more likely to be positive. Conversely, if we take our elements and again we combine the elements together in such a way, but we now place a column 5 element in there, we will find that our silicon or germanium in the crystal lattice form will align in such a way that we have the same type of configuration as we had with the column 3 elements. But we find that because of my column 5 element that has an extra electron, we find that we've got an extra electron. Again, everything was neutral when it went into this mixture, and because of that extra electron, this is called my N-type material. In other words, it's more likely to be treated as a negative charge. It's still neutral. This is also still neutral, but when we compare them together, we find this has more electrons and this has more holes. Holes are places where electrons can go, so this would be more likely to be treated as a negative, and this would be more likely to be treated as a positive. Now, when we combine the N and the P-type material, it's my P-type, and I'm combining it with an N-type. The P-type has excess holes. The N-type has excess electrons. So when I'm combining these two, I'm taking a material that is rich in electrons and combining it with a material that is rich in holes. Here where we combine these two materials, that is called my pn junction. Now what we find that happens is in my N-type material, all the electrons that are over here are attracted to the holes in my P-type material. Now as the electrons leave the N-type material and fill in on the P-type material, they are going to leave holes in the P-type material. And what we then find is in the N-type material, on this edge of my P-type PN junction, we will build up a layer of electrons that will form sort of a barrier that pushes electrons away this way and pulls holes into this side. And then what we find in the P-type material is we have a buildup of holes, which again forms a barrier within the N-type material. This area created between the N and the P-type material, that is called my depletion region. The depletion region. That barrier created in there will stop or control when current is allowed to flow through this component. When I take my PN junction, I've got my N-type material, I've got my P-type material. When I supply a negative on this side and a positive on this side, what happens is the electrons that are excess over on my N-type material is going to be attracted to that positive supply there, and the holes that are in my P-type material over here are going to be filled by the electrons from the negative supply. As a result, the depletion region that did exist will start to increase depending on the size of that supply voltage. So we find when we connected N-type material on the positive and the P-type material on the negative, that the depletion will increase. With a great enough increase in the depletion region will be able to take over the entire component, and then we do get conduction through the component, but that is not always intended or a good idea for the PN junction. This configuration for a PN junction is called reverse bias. When we've got our PN junction, P-type material, N-type material. Remember, we've got the depletion region in the middle over there. When we supply a positive on the P-type material and a negative on the N-type material, this is called forward bias. These electrons in the negative side will push more electrons from the N-type material into the depletion region, which makes it smaller on this side. The electrons in this P-type material on the depletion region over there is pulled away. That makes the depletion region smaller on this side. And if this voltage is big enough, then what happens is my depletion region falls away, and that will allow for electrons to flow through my PN junction. Now, putting that in graphical terms, let's call this my anode and that my cathode. When I apply a voltage across the anode and the cathode, I expect a current to flow through the anode and the cathode. When I supply a negative voltage across the anode and the cathode, we expect the same to happen. And when we look at my forward bias, I've got a negative and a positive connected on to my N and my P-type materials respectively. And when we've got a small voltage, as that voltage increases, we will find that there's a small leakage current that's flowing through the cathode or through the component, and that is because of the changing in the size of the depletion region. Once that depletion region falls away, we find that current will freely start to flow, dependent on the size of the voltage. Now, typically for a simple PN junction, that voltage over there occurs at 0.6 volts if these base materials are made of silicon. If we're using germanium, we find that conduction takes place typically around 0.3 volts. When we connect this PN junction into the reverse bias, we find that we will have a leakage current again because of the changing in the size of the depletion region, but we will find that eventually that depletion region takes over the entire PN junction, and then we get uncontrolled current flow that is allowed to go through. Now, for a typical diode, this happens above 600 volts. Now we know that current flow is directly proportional to the voltage. So if I've got 600 volts DC connected onto a diode, the amount of current that's going to flow is going to be so much that the diode is going to burn out. This is my typical characteristic for a diode. Note, it's not drawn to scale because, like I said, that's 0.3 and 0.6 volts, and this is typically at minus 600 or more volts. When we look at the construction or the symbol of the diode symbol is a triangle with a line that points in that direction. Now, all semiconductors somewhere does have an arrow. That arrow always points towards the N-type material, which means that arrow indicates that this is my cathode, which means that this side is my anode. So if this is my symbol and this is a forward bias, it means I've got a positive on the anode and a negative on the cathode, which means I will get conduction. And when we look at the reverse bias, there's my anode, there's my cathode. Reverse bias means negative on the anode and positive on the cathode. When looking at conduction, there's two possible ways to consider it. First way is electron current flow, where we're focusing on the flow of electrons moving from the negative to the positive. We can also look at current flow in the form of conventional current flow. Typically they do that in science, where they look at the flow of the holes from the positive side to the negative side. When considering semiconductors, it's always good to keep track of both methods or both directions of conduction.